The final hypothesis test we'll discuss in this module is the Chi-Square test. The application of the Chi-Square statistic that we'll talk about in this video is to test the null hypothesis that two criteria of classification, when applied to the same set of entities, are independent. To give you a sense of how this works, let's start with a silly example. Let's say we investigated the relationship between favorite brand of cola and favorite pet. From a practical standpoint, there's no reason to suspect that the two things should be related. Put another way, there's no reason to expect that preferring Coke over Pepsi would make you any more or less likely to prefer dogs over cats. So, if we went out and asked a whole bunch of people which cola they drink and which pet they prefer, we would not expect to see any difference between the groups. Or more accurately, we would not expect the proportion of people who prefer one pet over another to differ by cola preference. The two things are unrelated. Well, we can use this same logic and the Chi-Square statistic to test hypotheses about the frequency distributions between two variables of interest in our data. Here's how you can use the Chi-Square statistic to test for differences in proportions in SAS. Recall that we previously calculated differences in self-reported health by levels of personal doctor. Let's consider that table again, but this time with categories of PersDoc and GenHealth collapsed so that we can view it as a 2x2 table. There were 64 people in our sample. There were 24 with no personal doctor, and 40 with at least one personal doctor. And there were 41 in excellent, very good, or good health, and 23 in fair or poor health. So, if having a personal doctor is unrelated to self-reported general health, our null hypothesis, we would expect the same proportion of the population to be in excellent, very good, or good health, regardless of if they have a personal doctor or not. And by extension, we would expect to see the same pattern in our sample as long as it's representative of the population. As you can see here, among those with at least one personal doctor, 65% reported being in excellent, very good, or good health. Alternatively, among those without a personal doctor, only 63% reported being in excellent, very good, or good health. This may suggest that having a personal doctor is related to better self-reported general health. But before we conclude that this is true for all public health students, let's quantify how likely this finding is to be due to chance alone. We will do that with a Chi-Square test. In order to run a Chi-Square test in SAS, all that's necessary is to add the Chi-Square statement option to the table statement in the frequency procedure. Here, I'm also adding the expected option that will tell us what the expected frequencies are when the null hypothesis is true, and I'm also adding the no call option to suppress the column percents. This is just to make the table cleaner. The first table is similar to the typical table resulting from the frequency procedure, except this time we've asked SAS to include the expected number of people who would be in each cell if there were no relationship between PersDoc and GenHealth. The second table is where we can find the Chi-Square statistic. For this lecture, we will only worry about the first Chi-Square statistic, and again, I will only cover interpretation. Here we see that the Chi-Square value equals 0.0407, and the probability of observing a Chi-Square value this large or larger by chance alone, if the null hypothesis is true, is 0.8401, or about 84%. This is far greater than 0.05, which is the conventional level used to determine a statistically significant difference. Therefore, based on our data, we fail to reject the null hypothesis and cannot say that there's a difference in self-reported general health by personal doctor. I do want to point out one final thing. Whenever cell counts are less than 5, the Chi-Square test may not be valid. In that case, we should use Fisher's exact test instead. And because the Chi-Square test is non-directional, we should use the two-sided p-value. In this case, using Fisher's exact test would not change our conclusions. Here's a chance for you to practice testing for a difference between proportions. In previous modules, we learned how to describe differences between sample means and proportions. In this module, we took it a step further and learned how to draw conclusions about populations of interest based on sample means and proportions when certain assumptions are satisfied. Keep in mind that there are many scenarios which we did not cover, and the tools we learned in this module often fall short of giving us the ability to draw any conclusions about causality. But it's a good start nevertheless, and many of the basic principles and interpretations discussed in this lecture will apply to other procedures that you'll learn in the future.